Welcome to today's class on partial derivatives. Today we discuss interior point, boundary point, open region and closed region in the plane. First we define all these things. A point x0 y0 in a region R in the xy plane is an interior point of R if it is the center of a disk of positive radius that lies entirely in R. A point x0 y0 is a boundary point of R if every disk centered at x0 y0 contains points that lie outside of R as well as points that lie inside of R. The boundary point itself need not belong to R. So the boundary point need not be a point in R. The interior points of a region as a set makes up the interior of the region. The region's boundary points make up its boundary. A region is open if it consists entirely of interior points, and a region is closed if it contains all its boundary points. Now let us discuss what is the meaning of these things. You consider the region R and you consider a point x0 y0, and you can see that there exists a disk of positive radius. You can see that this is the disk of positive radius. So there exists a disk of positive radius which is contained entirely in the region R. So this is your region R, and you have this point x dot y naught, and you can see that this x naught y naught is the center of a disk which is contained in the region R. Therefore x naught y naught is an interior point. And set of all interior points. So all points of R except this blue curve make up the interior of the region R. Now we can see that what is meant by the boundary point. You consider a point here. You may consider any point on this blue curve. Then you have R is this region. You consider a point here. You can see that every disk centered at x0 y0 contains points of interior of R and points of exterior of R. Therefore x0 y0 is a boundary point. So that's the definition. A point x0 y0 in a region R in the xy plane is an interior point of R if it is the center of a disk of positive radius that lies entirely in R. So you can see that this point x0 y0 is an interior point by that definition. Now a point x0 y0 is a boundary point of R if every disk centered at x0 y0 contains points that lie outside of R as well as points that lie inside of R. So that is, you consider this point x0 y0, you can see that every disk, you may consider a disk of radius greater than this, and you can consider a disk of radius less than this. You can see that every disk centered at x0 y0 contains points of both interior of R and points of exterior of R. So this x0 y0 is a boundary point. Now the set of all interior points of a region R is known as the interior of the region, and set of all boundary points of the region R is known as the boundary of R. So you consider this region R, set of all points inside this R is known as the interior of R, and set of all points on the boundary, this blue curve, is known as the boundary of R. If R contains its boundary, we say that it is a closed region, and if R does not contain its boundary, we say that it is an open region. That is, if R contains only interior points, we say that it is an open region. Now we can illustrate this using an example. Now we consider the open unit disk, that is a set of all xy such that x square plus y square is less than 1. Remember, you are considering all points such that x square plus y square is less than 1. So you are not considering the boundary. So every point of this region R is an interior point. So this is an example of an open set. So you are not considering the boundary points. You are only considering the interior points. So this set, the set of all xy such that x square plus y square less than 1 is an example of an open set. It is known as an open unit disk. And you can see that every point is an interior point here. Now you consider set of all xy such that x square plus y square equal to 1. So you know that it is a unit circle, and you consider a point on the unit circle. You can see that every disk centered at that point contains both interior point of the disk x square plus y square less than 1 and exterior point of the disk. Therefore, set of all xy such that x square plus y square equal to 1 is the boundary of the unit disk. Here, every disk with a center, a point on the boundary, contains both exterior points and interior points of the disk. So it is the boundary of the disk x square plus y square less than 1. You can see that these boundary points actually does not lie on the region R. If you are considering set of all xy such that x square plus y square is less than 1. So this is an example of boundary. Now you consider set of all xy in R2 such that x square plus y square less than or equal to 1. You know that it is the closed unit disk because it contains its boundary. This is an example of a closed region because it contains the boundary of the region R. So set of all xy such that x square plus y square less than or equal to 1, which is the closed unit disk. It contains all its boundary point. So it is an example of a closed region. So this is an example of an open region, and this is an example of a closed region. Now we define a bounded region. A region in the plane is bounded if it lies inside a disk of fixed radius. A region is unbounded if it is not bounded. You can see an example. You consider the previous example. So you consider the unit disk. From the previous example, you can see that it is a region. It is an open region. Now you can enclose this region R inside a disk of radius greater than 1. So for example, you can consider a disk of fixed radius. So you can consider this disk. So it is a disk of fixed radius. You can see that this region R. So this is our region R. So we have enclosed the region R in a disk of fixed radius. So we can say that this region R is a bounded region. On the other hand, you can give an example of an unbounded region. For example, you consider the region inside the parabola y equal to x square. So you consider set of all points in the xy plane such that y is greater than x square. So you can see that this blue region is the region under consideration, and this region is unbounded because you consider, for example, you consider point A, it is 0, 5. So you consider the disk with the center A, and you can observe that no such disk can enclose this region completely. So for example, you consider this. So we are considering actually the disks with the center A and radius varying from 0 to 100. So no disk can enclose this region completely. So this is an unbounded region. The region y greater than x square is an unbounded region. You need not to take the center to be this point. You can take any point as the center. From here itself, you can see that the region is unbounded. For example, you may consider a disk with the center B and consider all disks, and you can see that no disk can enclose this region completely. So it is an example of an unbounded region. We do some examples. So this is the first example. Describe the domain of the function f of xy is equal to square root of y minus x square. So solution. We have f of xy equal to square root of y minus x square is defined if y minus x square is greater than or equal to 0. That is, the domain is set of all x, y in R2 such that y minus x square is greater than or equal to 0, or this is equal to set of all x, y in R2 such that y is greater than or equal to x square. So the domain is actually set of all points in the xy plane such that y is greater than or equal to x square. You know that this is the parabola y equal to x square. The region contains its boundary, so it is a closed region, and as we have discussed earlier, you cannot enclose this region inside a disk of fixed radius. Therefore, this is an unbounded region. So the domain of f of xy is equal to square root of y minus x square is closed and unbounded. And the parabola y equal to x square is the boundary of the domain, and set of all xy such that y greater than x square is the interior of the domain. So that is actually the set of all points inside the parabola. So this is the description about the domain of the function f of xy is equal to square root of y minus x square. So now we can discuss one more example. Describe the domain of the function f of xy equal to 1 by square root of 16 minus x square minus y square. So solution, we have f of xy is defined if 16 minus x square minus y square is greater than 0, or this implies 16 is greater than x square plus y square, or this implies x square plus y square is less than 16. That is, the domain is set of all x, y in R2 such that x square plus y square is less than 16. So it is actually interior of the circle x square plus y square equal to 16. So you can see that the blue region is the interior of the circle with the radius 4 units. You can see that this is an open region because every point is an interior point. So the domain is open and it is bounded because you can enclose this region inside any circle of a radius greater than or equal to 4. So it is a bounded region. So the domain is bounded. So this is the domain D, and you can see that all points of the domain are interior points. Therefore, the domain is open and bounded. So this is an example of a bounded domain and an example of an open domain. Now you can analyze the domains of the problems that we have discussed in the previous class in a similar way. And before that, let us see what is this function actually. F of xy is equal to 1 by square root of 16 minus x square minus y square in a GeoGebra. So first we plot the function z is equal to 1 by square root of 16 minus x square minus y square. So this is your function. It is defined over the region x square plus y square less than 16. So you may plot that also, x square plus y square less than 16. So you can see that the domain is the region x square plus y square less than 16. So this is the domain. You can see the domain. And so this is the domain. And the range is set of all z values. It starts from 1 by 4 to infinity. Z varies from 1 by 4 to infinity, and x and y varies over this disk. So that is the domain. The values over the z axis corresponding to this domain is the range. Here you can see that this point is 0, 0, 1 by 4. So we may put 0, 0, 1 by 4. So you can see that that point is actually point of intersection of this surface with a z-axis. You can see that. So this point to infinity, that gives the range. So you can see all these things together. First, this is the function corresponding to points on the xy plane. You have f of xy is this. Then you have this is the domain. You can see domain alone. So this is the domain, and you intersect the surface with this one. So you can see that the point 0, 0, 1 by 4 will be the point where the surface meets the z-axis. So there starts the range value. So corresponding to 0, 0, 0, you have z. Corresponding to other points, you are getting these values. So if you are considering this as the real line from 1 by 4 to infinity, so closed at 1 by 4, open at infinity, that is the range of the function. So this is the function, this is the domain, That is the explanation about that problem. That's all for today. Have a nice day.